Okay, so here is a quick half-life question. This is something you can see in real life. You're handed a wooden bowl, okay, and as soon as you see that you have something made out of wood, you know it's a carbon-14 problem. And it's claimed that this is prehistoric, so I don't know. Prehistoric to me means like at least 10,000 years old. It says you take a 5-gram sample from it, so imagine taking a chisel, you chisel a little bit off, and you put it next to your Geiger counter, and you get this, zero point 0.4 becquerel. So remember, a becquerel is 1 decay per second, 1 decay per second. Okay, so they say if half the mass of the wood is carbon, that's not an unreasonable assumption. There's carbon and hydrogen and all sorts of other stuff, but generally about half the mass of wood is carbon. How do you rate the claim that it's from prehistory? And then they say assume there's one carbon 14 for that many carbon 12s, and the half-life is 5730. Okay, so first of all, this number, the reason why they say assume that is because if you look in the atmosphere, that's what the ratio is in the atmosphere. And wood comes from trees, and trees gobble up carbon from the atmosphere, and they don't know what they're gobbling up, carbon 12 or carbon 14. But the point is, in the atmosphere, even though the carbon 14 decays, new carbon-14 is made every second by cosmic rays and all sorts of junk crashing into nitrogen molecules in the upper atmosphere. And this ratio stays pretty constant. But a tree, once it dies, doesn't absorb any new carbon. So it has only whatever carbon it has. And therefore, the amount of carbon-14, this will be the maximum amount of carbon-14 it could ever have, because after that it will decrease. So that'll be basically how we'll find our N naught, the initial number of carbon-14 we have. Okay, so how do we calculate that? Well, it's the mass of carbon divided by the mass per mole times Agravado's number, which is the number of atoms per mole, and then times the number of carbon-14 atoms per carbon-12. So if you grind out the numbers, the molar mass of carbon is 12. Now remember, I'm saying 12 here because all of the mass is basically carbon-12. Yeah, there's carbon-14 too, but it's like nothing. It makes up barely any of the mass. Okay, and then this is the number of atoms in a mole, and then this is how many carbon-14s for each carbon-12 you get, and you get this massive number. So 151 trillion, something like that. This 151 billion. So it's some huge number, but it's much smaller than this number anyway. Okay, so now that we know N naught, now we want to find the initial rate. That is the maximum rate we'll see, the rate right at the moment it died. Okay, so that's lambda times N naught. Okay, so lambda, if you remember, is log of 2 over the half-life, and then times N naught. That's the number we had before. Now, if you notice here, I'm finding lambda in terms of seconds. So this is the number of years, of course, but then I multiply by seconds, hours, days, in order to figure out how many seconds it is. And the reason I'm doing that, instead of just taking 5730 as the half-life, is because my problem gives me something in becquerels. And I want to compare the maximum decay rate I have to what's given in the problem. And in order to do that, remember, becquerel is decays per second. So I got to convert to seconds. So if I do that, I crunch the numbers, I get 0.5796 becquerel. So this thing, when it first died, had this decay rate. And I know that the decay rate is going to decline over time as the amount of carbon-14 declines over time. One quick thing to note is that in your book says R naught equals 0.23 becquerels per gram. And I could have started the problem just by saying that. But notice that if you take this number I have here, and you divide it by 2.5, why divide by 2.5? Well, because I have 2.5 grams of wood. Take this number, divide it by 2.5, and you're going to get that number. So I just show you this just to show that it's not a big deal to start a little further back and just deal with the quantity of wood you have. But I don't know, on the exam, maybe I'll just give you this. I haven't decided yet, but you should feel comfortable with both ways. Okay, so what do you do with this? Fine, so now we go to our half-life formula. So that says that the rate equals the rate you start with times this exponential decay. Okay, and so we can solve this for time. Let me just do that explicitly, just so. So R of t divided by R naught equals e to the minus lambda t. What do? You take the log of both sides. If you take the log of e to the something, It's just the something. So you get lambda t. And then there's one more step to go from here up to there. Okay, so if I do this, I get 3,066 years. Notice I evaluated this in years. I could have evaluated it in seconds, but I don't know how long ago prehistory was. And so when I calculated lambda this time, I didn't use this stuff. I just used this. You could have used the same number you had before, but then you'd get, I don't know, some number of millions of seconds or something. And how do we evaluate whether that's prehistory or not? Well, we're going to convert back to years, of course. And so I just said, don't bother converting in the first place. 3,066 years. So is this made by prehistoric humans? I say no. It's old. I would be delighted to own something this old. I would show it off to all my friends. But it is not prehistoric because, I don't know, this is around the time of the Iliad. The Greeks were around. The Chinese were around. Everyone. There was civilization. This isn't even the dawn of civilization. There was empires all over the planet, and they all had history and writing and mathematics and all sorts of other stuff. Okay, that's the idea of the kind of problem you're going to see. If you have questions, feel free to ask on the discussion boards.